Hello dear students, once again welcome you all for Power System Operation and Control class. So continue with the modeling of the automatic generation control. In the previous class we are seeing the generator model. So in the today's class we will continue with the load model. So while we are going for a building one model, that model we have seen one ALFCs consist of the governor model, turbine model, generator plus load model. All those models are togetherly connected. So till now we have seen the generator model. Actually generator plus load model is there. So this 6.20 figure gives us the generator model. Now I need to add the load model to this one. So this total model has become generator plus load model. So some loads exhibit variation in active power drawn with respect to the frequency variation. So that is given by delta PL frequency is equal to d delta omega, where d is called as the load damping constant, or the d is given by delta PL frequency divided by delta omega. That is delta PL frequency is nothing but the frequency dependent load. D is usually expressed in percentage change in load divided by the percentage in frequency change. Means if D is given as 1.5, let us say example I am giving you, its the value of D is 1.5, it means the load changes by 1.5% when frequency changes to a 1%. Got it? If the value of D given is 1.5 means the value of the load changes to 1.5% when the frequency changes from 1% value. The value of D is with respect to the particular load. If the system base is different from the nominal value of load, the value of D must be changed appropriately. If the system base is changed, values need to be changed approximately. So considering the 1000 MVA load with D is 1.5, this means the load would change by 1.5%. That is 1.5% of the 1000 MVA for 1% change in the frequency. Now, if system base were changed to 800 MVA instead of 1000 MVA, then D to be considered for new value. That D new is calculated is D new is equal to D into 1000 by 800, which is nothing but 1.875 is the new D. So neglecting the losses, the change in the electrical output of the generator, delta P is equal to the load. Therefore, we are writing delta P is equal to delta PL plus D delta omega, where the delta PL is non-frequency sensitive load change. This is the not dependent on the frequency. If it is delta PL frequency means the frequency dependent. This is non-frequency dependent, and delta D delta omega is the frequency sensitive load. So these things, if you are converting it into the Laplace model frequency domain, delta P of S is equal to delta PL of S plus D delta omega of S. So now the generator model is now shifted to the generator plus load model. That is by introducing the D, you can see both the figures are here only. 6.2 you can see model of generator is here. The same figure is now one D is connected here. So what is D, you know, just now we are seeing this one. Now by simplifying the block diagram, which are two there in the parallel side, this will become 1 divided by 2HS plus D. Okay, and thus this is totally called as a generator load model, or it can be once again rewritten as in block KPS by 1 plus STPS, where KPS is nothing but 1 by D and TPS is nothing but 2H by D. So 2H can be replaced by M, where both are in per unit, and the whole equation 6.21 can be rewritten in the form of KPS by 1 plus TPSS, whatever we are written in this 6.21 figure. Okay, or 6.22 figure, whatever we are written. Kp is the power system gain and TPS is the power system time constant. Okay, so we will see one problem here. Consider an isolated generator of 500 MVA M is equal to 8 per unit megawatt per unit frequency per second on the machine base. The unit is supplying a load of 400 MVA. The load changes by 1.5% for a 1% change in the frequency. That is the D value is 1.5 here. Draw the block diagram for the equivalent generator load system for an increase of 10 MVA in the load. Determine the steady state frequency deviation in the response. Okay, let's see the solution now first. So we can choose a convenient base here. So M is on the generator base and D is on the load base. So we'll choose one common base because both are on the different bases. Now you can see there, the generator base is 500 MVA and the load base is around 400 MVA. Okay, given the problem. So for on the common base of 1000 MVA, M values changes by 8 into actual base divided by new reference base. Now it is 4, and D is equal to 1.5 into 400 is actual and 1000 is now new. So we got it as 0.6. So this is M and D values we got. Now M and D values we will put it in the that equation. We know M is nothing but 2H. No, 2H is nothing but M. So where the 2H is there, where we will put M value, that is 4, and D value as 0.6 we will put. Okay, or we know that if you want to write it in other form, means that 6.22 figures KPS by 1 plus STPS. KPS is what here? 1 by D. 1 by D means what? 1 over 0.6, that is 1.667 will come, and TPS is the 2H by D, that is 6.667 will come. Now the figure changes to 1.667 divided by 6.667s plus 1, remaining delta PMS and delta PLS, that is comparing the prime movers and load changes. Okay, now so this is equivalent block diagram. Gain is now 1.667 and the time constant is 6.667. Now the load changes is 10 MVA they are given, means on the base of 1000 MVA 10 MVA change means 0.01 per unit is the change. So the mechanical power is remaining in same, therefore we can write delta omega S is equal to minus of delta PL of S into 1 over 4S plus 0.6, or by putting all these values we will get the equations 0.01667 by S plus 0.15 minus 0.11667 divided by S. Or if you take the Laplace inverse of this one, that will be converting it to time domain, then delta of omega t is equal to 0.1667 e raised to 0.15 t minus 0.1667. So now t tends to infinity and delta omega t tends to 0.01167. The steady state frequency deviation is minus 0.01667. The steady state frequency will be 1 minus this value, that is 0.98333 per unit. So 0.9833 per unit of the 50 Hertz is nothing but 49.1665 on 50 Hertz system. So response of the plot is given here. You can see this is the response of the plot. How the time changes, our frequency deviation is changes. Okay, so this is what one of the example regarding the our frequency deviation. Coming to the composite model now, when we build a ALFC model, we are interested in collective performance of all the generators connected to the system. So generator connected to the system are assumed to swing concurrently, so that we can represent them in a single equivalent generator with an inertia constant of M equivalent is equal to M1 plus M2 till Mn, whatever number of generators, driven by the combined mechanical outputs and the turbine connected to the generators. The block diagram shown in 6.25, the figure is the system for the N generators. You can see there. Okay, here delta PM1, delta PM2, like till delta PMN. Then the effects of the frequency dependency of the load are lumped into a single damping constant D, and the speed of the equivalent system is determined now frequency. The output frequency characteristics will depend on the effect of the droops of all speed governors and on the frequency characteristics of all the loads. For the system with n generator, the steady state frequency deviation after load change delta PL is given by delta FSS is equal to minus delta PL divided by 1 by R1 plus till 1 over Rn plus D. This is what the regulation and all we are knowing. So this is the changes in frequency, and this is the block diagram is of the composite model, where we can write that is delta FSS is equal to minus delta PL divided by 1 by R equivalent. Here 1 by R1 to 1 by Rn is taken as 1 by R equivalent plus D. So we are see how to write the R equivalent is 1 over 1 by 1 R1 to till 1 by Rn. D is the composite load damping constant. The composite frequency response after response of the system is given by beta is equal to minus delta PL divided by delta Fm, or which is nothing but 1 over R equivalent plus D, where beta is referred to as stiffness of the system or frequency bias factor, and the unit of beta is megawatt per hertz. The composite regulating characteristics is 1 by beta. If there is a increase in the load by delta PL at nominal frequency, then we have to increase the we need to increase the increase of the delta PG in the generation, and reduction of the load delta PD due to the frequency dependence of the load. Therefore delta PL is given by delta PG minus delta PD, or delta PG is given by minus delta F by R, or delta PD is given by D delta F, or therefore delta PL is given by minus delta F by R minus D delta F, which is can be written as delta F into minus 1 by R minus D, or delta F is equal to minus delta PL by 1 by R plus D. So this is regarding the composite model of the different loads. Okay, so in this video we are studied regarding load model, and togetherly generator plus load model we are seen. In the next class we will see about the turbine model and the complete model of the ALFC. We'll see. Okay, thank you.